Okay, hello. So today I attended a probability class in college, and the professor talked about the Bertrand paradox. So I was just thinking about that, and I had some thoughts, and I just thought, it'd be fun to record it. So yeah, so just what is the Bertrand paradox? Basically, you have a unit circle. So r is equal to 1. The radius of the circle is 1, and you're going to draw a random chord on it. So that's kind of like the trick of the question. You're going to draw a uniformly, which roughly translates to equally likely, like uniformly sampled random chord. So you're gonna take a random chord. What is the probability that the length of the chord is greater than root 3? And so you might be like, okay, what is this root 3? It feels like a very random number. The geometric motivation for that is you inscribe a equilateral triangle inside the unit circle. Then this thing's side length would be root 3. So the question is, what is the probability that if I draw a random chord, the length of the chord will be more than the side of the equilateral triangle? So this is the problem. Now let's try to understand what this uniformly sampled random chord even means. So and if I mean I'm just going to assume you've already seen this problem. Okay, so we already know that there are like some 3 different at least answers to this problem. So half, 1/4, and 1/3 are, I guess, 3 of the most well-known possible answers to this problem. Why do we get this problem? Like in JE and all, we never had this issue, right? Uh, like I said, if you kind of think about uniform sampling as saying everything in the sample space is equally likely, then we never had this problem in JE. Uh, if you have a set of possible outcomes in your sample space, you will. So, for example, let's say you're tossing a die, rolling a die, then you would be like, the possible outcomes in my sample space are 1, 2, 3, 4, 5, 6. And then I will assign a number p to each of these events, like each of these outcomes. And because why am I assigning the same variable p? Because they're equally likely, and the normalization criteria tells me that p must be 1/6. So that very simply works out, right, in the JE sense. Like equally likely has a very simple and nice meaning. You just put p probability for everyone and then normalize it, which if the size of your set is n, then each fellow is 1 by n. So that's sort of where the idea of number of favorable outcomes by total number of outcomes stems, right? But if you think about a slightly harder, or not harder, a slightly, let's say harder question, which is, what if this sample space omega is not a discrete thing? Not only discrete, it's not even countably finite. Like you can't even enumerate everything like natural numbers. There is, so what I mean is, for example, let's say 0 to 1. Okay, so you have some number q which is like 0 to 1, and every number is equally likely. Like q is equally likely to take 0.5, q is equally likely to take 0.51, q is equally likely to take 0.1, q is equally likely to take 0.9999994. It is equally likely to take all these numbers. So that is what uniformly sampled is supposed to mean. But I mean, and intuitively it's like, okay, equally likely is like, it makes intuitive sense that all these numbers are sort of this way. But then if you try to associate a JE way of thinking to this, where you put p for everyone and then normalize it, then you sort of get that every number should have a probability 0. Then if everything is 0, then sum of 0 is 0. And so it's not as straightforward as you do with JE. So basically what I'm trying to say is, equally likely is, or uniform sampling is a bit interesting when the stuff that you're doing is kind of there's a continuity involved in it, like it's a number from the real number line, or if it is supposed to be a point within a unit square or something, then you have to stop thinking in terms of associating. Yeah, you cannot try and put probability p for every point and then divide and then do 1 by p. I mean, p is equal to 1 by n. You can't do that. So that, and so what we so that's sort of where the problem stems in this Bertrand's paradox. That's not the core problem. I think the core problem is something slightly more than this, but that's sort of the foundational problem. That's not just discrete. If it was discrete, then we can just easily do what we did in JE, right? Just do 1 by n and call it a day. Like uniform sampling is just saying equally likely, so do 1 by n and go off. So that doesn't work here because everything is continuous and stuff, right? So yeah, now within J also we did this, and a sort of another intuitive way of thinking about probability is in terms of ratios. So if I ask you something like, let's say there's a unit, let's just take this same unit circle, right? And then I tell you that a dart is randomly thrown inside this circle. So the dart, so essentially a point is uniformly sampled within this circle. So that's a very sensible thing to say, right? Like every point within this circle has an equal likelihood. I mean, equal chance of being selected. So some people who have studied like more crazy probability might slap me, I guess, because it's continuous and you can't talk about the probability of a single point in this plane. But yeah, for the sake of like I think it's still useful, like you get intuition. So yeah, every point is equally likely to be chosen. What is the probability that the point lies inside the triangle? So then you would stop thinking in terms of points, and then you will use fractions. So what fraction of area is occupied by the equilateral triangle? And then you can say some root 3 by 4, I think would be the answer. So the shift is to stop thinking in terms of like summing up a bunch of points and switch to notions of fractions. Similarly, if I tell you what is the chance that a number which is like uniformly sampled, like every number within 0 to 1 is equally likely, what is the chance that the number I get is between 0.4 and 0.9314? So then the answer would simply be, what is the equivalent question would be, what is the fraction of the length which is occupied in here? So then you can say 0.5314 by 0.4 is the answer. So sorry, by 1 is the answer. So basically this number is the answer. Okay, so you start shifting from thinking in terms of points to now, and what do I mean by points? I mean elements in a sample set in your sample space. You stop thinking about that, and instead what you do is you start thinking in terms of ratios of areas or ratios of lengths and stuff like that, like basically a fractional quantity. And a good way to do this fraction is just what we did, right? Use areas, use lengths, use these use these geometric things. And like a nice way to do geometry is to use coordinate geometry. So you can think about, basically you can think about it like you have your sample space with a bunch of elements in it. With each of those elements you associate a point depending on the situation that you have, and then you can use fractions to figure out what the probability should be. So in the case of all points in the circle, then like I said, every point in the circle is like equally likely. Everything. So what am I saying? Every point in the circle is equally likely. What is the chance that the point epic is within the equilateral triangle? Then you can sort of think of your sample space as points x comma y such that x square plus y square is less than or equal to 1, and then you can put the equivalent geometric conditions, and then now this is a geometry problem and you can get it. I mean, it was a geometry problem to start with, but I'm saying now you can use fractions to solve it. Okay, so now let's come to this chord question. So what is your sample space for this chord question, right? Now since there is some kind of rotational symmetry, let's just kind of fix it. Let's just say that there's a coordinate plane, there's a coordinate axis. This is the circle x square plus y square equal to 1, I'm like fixing my axis and stuff, just to like give myself peace of mind. Otherwise my brain keeps thinking, oh, I can rotate the circle, I can rotate this around, all these things. I already said x square y square equal to 1, so I'm just removing r equal to 1. Let me just remove this as well. So yeah, so now so what is your sample space? Your sample space is basically set of all chords, right? And the set, so what is this like number of elements in the sample space? It's infinity, right? It's not a finite number. So again, now you cannot do 1 by n. You cannot say I dropped my pen. You cannot say that all my chords are uniformly sampled, which means it's equally likely, so I will do 1 by n and call it a day. I mean, then you will get stuck, as we discussed earlier. So now you have to sort of think about a fractional notion. So a nice way to do that is to associate a coordinate, or like even if it's a single number, it's a coordinate on the number line, right? So a good way would be to associate a coordinate with each chord, and that's sort of where the whole like paradox comes in. Is how would you associate a point for that chord, and then depending on how you have done that association, you will get different answers. So to get the answer of half, the point that you use to describe a chord is basically the radial distance from the origin and theta. So then the plane that you will, the set of all points would be r will range from 0 to 1, theta will range from 0 to 2 pi, r goes from, and the sort of condition is that in order for that chord to have a length greater than √3, it must be at a radial distance smaller than half, and the theta can be anything, theta can be anything. So in terms of fractions of area, it's this fraction of the area, so the answer is half. So that's how you can get the answer of half, by using this as the way to describe the coordinate that corresponds to a chord. Another way to talk about the coordinate that corresponds to a chord is simply by using x mid comma y mid. That's it. This is a coordinate that describes the chord, right? So, and the condition that you would need is that x mid squared plus y mid squared must be less than half, right? In that case it will be. So now the geometric situation that this would correspond to is x mid can range from 0 to 1, y mid can range from 0 to 1, so it's a circle. X mid squared plus y mid squared less than equal to half is this half radius circle, so 1/4 is the fraction. Then the third way of describing a chord is you pick a single point on the circle, so you pick some point on the circle, and then you need to, the second point that you pick for the chord must be within the 60-degree arc that it has. So now how you're describing a chord is by using two angles, let's say phi 1 and phi 2. Phi 1 is free, it can be anything in 2 pi. That basically decides your first point. Then phi 2 is anything within, phi 2 has a range of pi, right? It has a range of pi, and we want it to be within pi by 3 to 2 pi by 3. So now this corresponds to a different picture. This is phi 1, this is phi 2. Phi 1 can range till 2 pi, this can range till pi. So this will be your thing. And your phi 2 must be between pi by 3 and 2 pi by 3. So this is the corresponding area. So the fraction would be 2 pi times pi by 3 divided by 2 pi times pi. So that gives you the answer of 1 by 3. So that gives you the three different things. So essentially, why am I yapping all these things? You guys already know, I guess, the logic behind this. The idea is just simply the way you have associated a coordinate for each of these chords is varying in each of these cases. And I think that is, so that hopefully, like, I thought I got a better understanding of the problem through this way of thinking. So hopefully even you did. For those who have studied like multivariable calculus, there's an analogous experience that you will face in multivariable calculus, right? So let's say you have a function f of x comma y, z is equal to f of x comma y, let's say. So something z is equal to f of x comma y, and you want to find the volume under this, then you will simply do a double integral and put dx dy. Now let's make a more general question, I guess. So let's say w is equal to u comma v. Then you would do, I'm using uv to just dissociate myself from thinking about xy coordinates. These are just some general random coordinates, who cares, right? So this is the correct thing in this coordinate system. But then you would have done, if this, so basically what I'm trying to say is, if you want to do, if you want to integrate with xy, you will do dx dy. But if you switch to some polar coordinates, you won't do dr d theta, right? You will switch to r dr d theta. Like this extra factor of r will come up in order to get the correct thing. So basically, in a very loose sense, these two fellows are actually just the same, but they're off by a single factor. In this case, that factor is dependent on a coordinate, so the answers will not always be off by the same constant factor. But sometimes it, like for example, if my coordinate transformation is some linear transformation like this, y by 2, then this extra factor would always be a constant number, and these two areas will be off by a constant factor. So I think just like that, you can, all these answers are equally correct. It is just to go from this coordinate system to this coordinate system, this Jacobian factor will come up. And we did not account for that Jacobian factor over here, so we are getting different answers. Correct? And so if somebody comes and asks you, wait, hey, is the dx dy answer correct or is the dr d theta answer correct? No, I mean both of the answers are correct, right? The only reason why you will lose marks if you exclude the r in the exam is because we take dx dy to be the standard, and we want to find all the other areas with respect to dx dy, right? If somebody tells you no, dr d theta is the standard, then you will have a corresponding factor over here. Maybe it will be root of 1 plus x square y square. Actually, it's an interesting question. I never thought about what the reverse factor would be. But some factor will be there, right? So it's not like this is the correct area, this is the correct integral, this is the wrong integral, or this is the correct one, this is the wrong one. There's nothing like that. It's just the xy system is defined as a standard. Why is r theta describing a circle? Why can't I say r is this, theta is this? This is what an r comma theta looks like. Why can't I say it's a rectangular coordinate system? Because I've defined xy system to be sort of the standard. That's why r theta takes the shape of circles and not like rectangles or something like that you would imagine in xy system, right? Like if you talk about a unit square in xy, you will think this. Unit quantity in xy, you'll think this. But a unit quantity in r theta system is probably like some kind of circular segment like this, right? So yeah, there's no area that's correct or wrong. It's just this is defined as a standard, and within the xy system, if you map each r comma theta to its corresponding x comma y, it would take the shape of concentric circles. An interesting question that I haven't thought about is, what would, if I call r theta as my standard, what would xy look in r theta? That's an interesting question, right? So it is completely symmetric in theta, so it would just be a function of r, which is duplicated many times in theta, I guess. And r is basically root of x square plus y square. I mean, accordingly you can figure it out, bro. For now I'm going to stop the video because it's 12:30 and I have class at 8 a.m. Bye.